Okay, welcome everybody to the Azure and AI show. Um, we have Precious is going to do a talk for us there on some insights into cloud computing and virtual machines. And we also have um, Hamida, and she is going to do some stuff on architecting .NET microservice in Docker ecosystem. And then we have Harry. He's going to do some how AI and cloud automation refines capital assets. And hopefully we'll have Manny join us, and he's doing stuff on building agentic AI workflows with XAI and Vertex AI. So that could be interesting one. So hopefully he turns up. Just 1 second now, and I'll share my screen. Can you see my screen there?
Yes.
Yes.
Yes. Okay, so Precious, I'll start the slideshow and you can tell me to move on to the next slide when you're ready. Okay. There you go. Yeah, Precious, can you take over there now if your first slide is up?
Okay, yes. Thank you, everyone, and welcome to AI and Azure Show. My name is Precious, and I'm a cloud infrastructure specialist focused on Microsoft Azure. I also, through my platform, Cloud and Beyond, I also simplify cloud computing and document my learning journey because I am still on my learning phase. Then also creating platforms for beginners to as a learning space. So today I'm going to treat Azure Virtual Network Pairing while using virtual machine to show the connectivity around it. Okay, thank you, Frank. So we are understanding Azure Virtual Network Pairing. 1 minute, please. Someone is at my door. So, yeah, understanding Azure Virtual Network Pairing and how the virtual network pairing enables secure and private connectivity in Azure or in any in cloud environment. So on my net, can I have my next slide? So now the first question you should ask yourself when you hear about virtual network pairing is what is virtual network? Virtual network is a resource in Azure that enables connectivity and communication between virtual networks in Azure environments. I'm trying to run this slide within just 5 minutes because I have a demo to um, present. So I'm going to go as fast as possible. So please, can I have my next slide?
There you go.
Now, now, now for the resources in Azure to communicate securely and privately, that is where pairing comes in. Pairing is the service in Azure that allows two or more virtual networks to communicate effectively through Microsoft private connection. So now, when you talk of pairing, pairing is a secure private network, like I stated on my slide. There is no public internet routing. It's a direct connectivity between the virtual networks in Azure. Next one, please. Now, how virtual network pairing works? By default, you can scale up to 500 VNets, virtual networks in Azure. Then, I swear, the connection is non-transitive. That is to say, when you have a virtual network, just a virtual network A or a virtual network B, and as well you have a virtual network C, and A is connected to B or C, that doesn't automatically make B and C to connect to each other. There must be a direct connection between each virtual networks in Azure. That's why I stated it's non-transitive. Then it's bidirectional, meaning when you configure a virtual net during your configuration, if you allow virtual network A to access resources in virtual network B, if you want to configure a bidirectional setup, you must as well allow virtual network B to gain access to resources in virtual network A by clicking on the access button. Then there is also a one-way connection. One-way connection is one-way configuration is when virtual network A is allowed to access resources in virtual network B, but virtual network B is not configured to access resources in virtual network A. Speaking of that, I'm going to connect it to two separate office buildings. You have Office A and Office B, right? People in Office A are allowed access to Office B to do whatever they want within the building, but people in Office B are not able to get into Office A. This is the one-way connectivity. Then the bidirectional is when the two persons in the both offices are able to communicate and connect bidirectionally. And the next slide, please. So now there are two types of virtual network pairing. You have the regional and you have the global. The regional is when you have two or more virtual networks in the same region. And the global virtual pairing is when you have two or more virtual networks connected through pairing in different regions. You may have virtual networks existing in the same region, that is East-US, different virtual networks, right? Then you would have a virtual network living in East-US and West-US or East Australia East. They can as well communicate through pairing. That is where you see regional pairing and global pairing. So going over to the next slide, what I have there is the key benefits of virtual network pairing. You have low latency. Low latency, that is to say the data transfer is very fast. The traffic is very fast. There is no limit to the traffic while the traffic is running. There is no downtime. Then you have a high bandwidth. The high bandwidth meaning the capability of the network to transfer data, larger amounts of data. It is secure and private. That is to say, the connectivity and the communication exists only within Microsoft's backbone connectivity. The next slide, please. Now, during the connectivity, there must not be IP address IP address space overlap. This is one of the things you should look out for while configuring a virtual network pairing. And another thing is NSG, network security groups. They as well control the traffic that flows in and out of paired virtual networks. I am supposed to read out my slide, but because of my time, I'm trying to be as fast as possible. So you have to note that NSGs can as well influence the flow of resources in and out of paired virtual networks. And let's go back to the next slide. Now, you have the flexibility of address space management. The flexibility of the address space management simply means that you can resize the address space in a paired network. Now, during this resizing, during this configuration, you wouldn't experience any form of downtime. That everything is flexible within the configuration phase. Nothing stops. Everything still moves seamlessly. So with this, I can still go over to my next slide to see what I have there, and before we get into the demo. confirming connectivity. Okay, one of the ways to confirm connectivity of a virtual network paired configuration is through Azure Network Watcher topology feature in Azure. So this is one of the ways. There are so many ways to confirm it, which I am going to practice out during the demo session. There are so many ways you can confirm this, but one of the ways I stated out, because through this feature, it can provide a visual representation of your network configuration. That way you can see your VNets where if you have virtual network pairing that lives in different region or in the same region, you can as well see the visual representation. So the key takeaways from all I have said so far is the virtual network pairing is secure and efficient. Azure VNet pairing offers robust private network connectivity, communication between resources or virtual networks in Azure. Operational benefits ensures low latency, like I mentioned earlier, high bandwidth and zero downtime. Flexible communication supports regional and global connection with customizable flow. Enhances control. That's where NSG and Network Watcher comes in. So with this little explanation around Azure Virtual Network Pairing, I am going to go over to the demo. Now, I'm going to share my screen so if that will be possible. Okay, I can actually share just one of my screen, not the entire screen. All right, we are on. I believe you can see my screen right now.
Yeah.
Great. Now I have already, because of time, I had to deploy the virtual networks in 2 different regions and as well create a resource in the both virtual networks, which I'm going to show you right now.
Okay, we can see the screen there now, yeah.
So this is the resource group where the resources are. This is my first VM, my VM1, which is in East US. This VM is in East US, and I have already created the virtual network as well is in East US. Now this is my VM2, which is in West US, and the virtual network I used in this configuration is also in West US. That is to say, so I'm trying to go over to the virtual networks to. You can see my VNet 1 is in East US, and my VNet 2 is in West US. So I'm going to configure a pairing amongst these 2 VNets here for us to confirm everything I have said so far. So I am on my VNet 1, which is in East US. I'm going to pair this VNet to VNet 2, which is in West US. So I'm just going to start off with the configuration. VNet. So now, this is the pairing name, the pairing link name. What I just wrote here is the pairing link name. This is my subscription. This is the virtual network I'm trying to connect to. I'm trying to pair to through this VNet 1. I'm trying to pair to VNet 2. That is why I did this. Now, this is allow VNet to access VNet 1. Allow VNet 2 to access VNet 1, meaning that VNet 2 can be able to access VNet 1, communicate securely, and share resources within VNet 1. Allow VNet 2 to receive forwarded traffic from VNet 1. If there are forwarded traffics like the NDAs, VNet 2 can be able to receive it when it's being forwarded from VNet 1. Now, with my this I cannot be able to, this I know this wouldn't work for me. Allow gateway or route server in VNet 2 to forward traffic to VNet 1. This is where we, if we have gateway connection, which I don't have on my platform, on my portal right now, and the same here too, to make use of the gateways from VNet 2. Now, when I said it's bi-directional, whatsoever configuration you have here, you should as well enable it here. When you enable it here, that means it's going to be bi-directional. But if I uncheck these two boxes, there would be no bi-directional connectivity. It would just be one-way connection. I mean, when it comes to this, allow VNet 1 to receive forwarded traffic. If I as I uncheck this box and check it here, it's only VNet 2 that will be able to receive forwarded traffic from VNet 1. VNet 1 will not be able to receive forwarded traffic from VNet 2. So I will go ahead to type the name of this pairing, which is VNet 1 to VNet 2. So I'm going to add this connectivity, and I'm going to wait for it to deploy while we confirm if the connection is fully synced. We're going to my network is slow. It's actually restarting this. You have to bear with me. My network is really slow this evening, but I have to do this. So this is it. The pairing is fully synchronized. It's connected to VNet 2. I mean VNet 1. It is actually connected to VNet 2. So I talked about confirming the connectivity through Azure Network Watcher. So I'm going to go check the topology of Azure Virtual Network Watcher to confirm if the connectivity is truly there, which is there, but we just need to be sure. Then after this, I'll go over to my virtual machine to ping the both IPs to confirm that they can actually communicate securely through Microsoft backbone connectivity. So this is it. It's going to expand this. So this is the pairing. I wanted to okay, yeah, it's out now. I wanted to expand it so we'll have a good view of it. Yes. So this is my VNet in East US, and this is my VNet 2 in West US. There is a connection here this connection here means that the two virtual networks are communicating. There is a connectivity between them. Now I'm going to go over to my virtual net machines to ping the resources to see if to confirm that the connectivity is truly there and the two resources can actually communicate with each other. Okay, I guess my time is up. Should I go ahead?
No, it looks okay. If you want to,
Hello?
if you want to ping the things, that's okay. But you got it to work anyway. We see
I just looked at my time and it's up.
Yeah, that's okay. We actually
what?
see you did get the VNet working. Can you hear me okay, Precious?
Okay, so I'm trying to ping both virtual machines in different. Yes. I can hear you, but I didn't get what you said earlier.
No, that's okay. You can carry on if you want to ping the machine.
Okay. To start virtual machine. I guess I need to leave it at the point where we've said that the paired connectivity is actually configured because my internet is very slow and it's not allowing me to turn on the virtual machine.
That's okay, Precious. Thanks very much for your presentation and thank you.
You're welcome.
And there's no questions coming in for you, so we'll hand her over to Hamida. I have your screen here.
Okay.
And there you go, architect.net microservices. There you go.
Yes, thank you. So I am Hamida Erbai. Hi, everyone. I'm distinguished integration architect working always with cloud, containers, and large-scale digital transformation. And today I will show you how modern architecture with Docker help build faster, smarter systems. So if you'd like to continue this discussion after the session, you can find me on LinkedIn or Medium blog. I'm sharing some YouTube video also. I have my personal blog also that you can uh, that I'm sharing here in the slides. So we start in the beginning to talk about microservices architecture. So the implementation of .NET application, this is the example that we work on today. And we will use Docker containers. We see the difference between microservices, containers, how we can deploy it on the cloud, specifically with Azure. And we have a lot of demonstration. We show you how you can set up your development environment locally, and we will see what you need to deploy in the cloud. So we start talking about microservices. Microservices are a natural evolution of service-oriented architecture, but there are differences between microservices and service-oriented architecture. Let's see from some characteristics of microservices. In microservices architecture, services are small and dependent and loosely coupled. Each service is a separate code base, which can manage it by a small development team. And services can be deployed independently. A team can update an existing service without rebuilding and redeploying the entire of your application, which means that services are responsible for persistence. For example, if we have a database, so we can have some microservices for your own data. They can persist your data or any external state. This differs from traditional model where a separate data layer handles data persistence. Services communicate with each other by using well-defined APIs. Internal implementation details of each service are hidden from other services. Services don't need to share the same technology stack, libraries, or frameworks, which means that you have big application, e-commerce application. You can have some, let's say, services or microservices built in .NET application, others for AI built with Python, for example, some microservices that will persist your database. So it's related to your database. So we have a lot of technologies in the same applications. Besides of the services themselves, some other components appears in a typical microservices architecture. We have also the management components. So we have multiple microservices. So we need a centralized part. We call that the management component that is responsible for placing services on nodes, identifying failures, rebalancing services across nodes, and so forth. We have also service discovery that maintain a list of services and which nodes they are located on. It enables a service lookup to find the endpoint for a service. We will talk also about that in the next slide about API gateway. So we will see what's the role of API gateway, but it's our entry point for the different clients. Microservices are very similar to beehives. Within a hive, 1,000 of bees coexist and help each other for a single common goal, the survival of the colony. The queen, the workers, and the drones each have their particularities and must therefore assume very distinct tasks. Now we'll see the microservices architectural style. We will talk about API gateways. As you can see, the client, the identity provider, we'll talk about all these components. So developers consider microservices as architectural style that promotes the development of complex application as a suite of small services based on business capabilities and multiple independent subsystems in the form of autonomous services. In these pictures, we will see that different components. So let's start by the first one, that is the management that we already talked about. The management part maintains the nodes for the services. We have the identity provider that manage the identity information and provides authentication services within a distributed network. We have also the service discovery. It keeps track of services and service addresses and endpoints. And we have the API gateways that serves as a client's entry point, the single point of contact from the client, which in turn returns responses from underlying microservices and sometimes an aggregated response from multiple underlying microservices. If we see our picture here, we have API gateways that sits between clients and services. It acts as reverse proxy, routing requests from client to services. It may also perform various cross-cutting tasks such as authentication, SSL termination, and rate limiting. If you don't deploy a gateway, clients must send requests directly to front-end services. You can imagine if you have a lot or big number of microservices, what can happen. It creates coupling between the client and the backend. So the client needs to know how the individual services are decomposed, and that makes it harder to maintain the client and also harder to refactor the different services. And the API gateway can perform other cross-cutting functions like authentication, logging, SSL termination, and load balancing. So, when we talk about microservices, sometimes we hear about containers, but microservices is completely different from container. A container is used for resource allocation and sharing technology. It's something like DevOps people get excited about. A microservices is a software design pattern. It's something that developer get excited about. So we understand the difference between them and specifically about the person where they focus on. In other words, so we can sum this as microservices are about the design of software and containers are about packaging software for deployments. So we can choose whether to use a container for hosting microservices, but to get full value from both, it's significantly better to run microservices within containers. Deploying an entire application to a single VM introduces single point of failure risk, whether or not microservices architecture has been used. But spreading the application through microservices across multiple containers results in fully exploiting the value of both by providing resilience as well as agility through scaling and improvement targeting specific services without any impact to the entire of your application. Flexibility is also introduced in that developers can write application in the language of their choice, since the container will allow them to deploy across whatever environment is provided. Efficiency comes from containers using less resources compared to virtual machines, and an added benefit comes in the form of security through isolation and a broader attack surface that limits the impact should a single microservices or container be subject to a security breach, such as a hacking attack. Now let's talk about containerization, that is an approach to software development in which an application or service, its dependency and its configuration abstracted as deployment manifest files, for example, are packaged together as a container image. The containerized application can be tested as a unit and deployed as a container image instance to the host operating system, just as shipping containers uh, all that allow goods to be transported by ship, train, or truck, regardless of the cargo inside. Software containers act as a standard unit of software deployment that can contain different code and dependencies. So, containerization software it's the way it's a way that enables developer and IT professional to deploy them across different environments with little or no modification, which means that the problem that the developer say it's working in my local machine, but I need to do some configuration in the production. It doesn't work in the production environment. With containers, we can resolve this problem. Because containers also isolate application from each other on a shared operating system, and containerized application run on top of container host that it turn runs on the operating system. It can be Linux, Windows, and containers therefore have a significantly smaller footprint than virtual machines images. Each container can run a whole web application or a service or in this, for example, it can be we can have a container for an application web, a container for a service API, and they are all containerized application or services. Inside we will see which technology that we can use. So when we talk about Docker, we talk about containers. Docker comes here. Here we see the difference between Docker container. We already talked about container, but to create container, what we need. So Docker container is the virtualized runtime environment used in application development. As we already mentioned that in the definition of containers. But with Docker, we are able to create, run, and deploy applications that are isolated from the underlying hardware. A Docker container can use just one machine, share its kernel, and virtualize the operating system to run more isolated processes. So Docker containers are lightweight. But how we can create our containers? Here we talk about image, Docker image. Docker image is like snapshot in other types of virtual machines environments. It's like a record of a Docker container at a specific point in time. Docker images are also immutable. While they can't be changed, they can be duplicated, shared, or deleted. The feature is useful for testing, for example, new software or configurations, because whatever happens, the image remains unchanged. And containers require an existing runnable image. They are dependent on an image because they are used to construct runtime environments and are needed to run an application. For example, if I would like to create an application.NET, so we create our application, but if we need to containerize that application, we need an image of .NET framework, for example, .NET SDK. We will see that after when we create our Docker file. But we need an internal image, and we find all images in the website of Docker. We call that Docker Hub. We find all images that you need to use it. You can use an image of operating system, an image of any framework, and you create your own image. Let's say how we can do that. So let's start by an application. I have my application .NET or any other language, and we create a Docker file, called Docker file. Each Docker file, it's a script composed of various commands. It's like unstructured. We have arguments listed successively to automatically perform actions on a base image in order to create or form a new one. They are used for organizing things and greatly help with deployment by simplifying the process start to finish. A Docker file starts with defining an image. This is the image that we need to use it from Docker Hub. We start by from. which the build process starts, and followed by various other method commands and arguments. We can have conditions. In return, provide new image which is to be used for creating Docker containers. So as you can see here, we have our Docker file that will be inside our application. If we build, this image, we use build. And if we run the image, we are able from the same image to create one and more than containers. So if we take a look about how we deploy these containers, so we use containers only for microservices, or are we able to use them for an existing application, old one, for example, for all technologies? So you may want to use Docker containers just to simplify deployments, even if you are not creating microservices, okay? For example, perhaps you want to improve your DevOps workflow with Docker containers, can give you better isolated test environments, and can also eliminate deployment issues that can be caused by missing dependencies when you move to production environments. In cases like this, even if you are deploying a monolithic application, it makes sense to use Docker. I give an example for .NET Framework, the old one, not .NET Core, for example. You have an application with, for example, .NET 5.5, 4.5, for example, so it's old one, .NET Framework. You are able to create a container, but the operating system should be a Windows operating system, because we can't run old one on Linux operating systems. So it can be one of the scenario to migrate your existing application. The old one, you start by containers, and next you can move to .NET 10, for example. And so we are able to create containers from existing, for monolithics, for lift and shift. We talk about lift and shift to containers for the cloud also, or to create multiple containers with microservices. And we use orchestrator to orchestrate between them. With Docker, we have orchestrator like Kubernetes. We use them to orchestrate between the different Docker containers. So we present some examples. What we need to run all these examples, we need to have Docker Desktop. It's free. It's available for Mac, Windows. You can download it without any account, but if you'd like to use some the images, internal images, or to deploy on Docker with your own image, because you are able to deploy your own image to be used for free, so for as a private repository. So you can create an account. It's free. For personal use, it's free. So for enterprise, we can have multiple plans. It starts with free, and it depends from the enterprise, the organization, or the company. So it can start with professional to enterprise. We have different plans. So we need to install Visual Studio Code. You can use Visual Studio 2026, for example, the last one. So and the previous version. So it's up to you. We need to have an Azure account, because in the last demo we will try to deploy on Azure Container Registry and Azure Web App also. So as a container, we will just create one container in our example. If you prefer using command lines, so you can use PowerShell, Azure Cloud Share. And for Visual Studio Code, we need to have the C# extension already installed, Docker extension already installed, and Azure extension already installed. If you would try to debug, for example, you'd like to debug your Docker file, we will see which one, which extension, but here we need the Docker DX extension to add it in Visual Studio Code. So before we talk about Docker, I want to show you something very simple. This is the example of today. This is a .NET application, nothing fancy, no Kubernetes. You don't have no Docker, no container, just normal enterprise app. Let's think about that. This very simple system, but it presents a pattern we see everywhere in enterprise platforms. It's a control system, something that manages a shared state. So here it's a traffic, really, it's really a small traffic light. This traffic light is not a toy here, but it presents states, the same kind of state that exists in every real system. So if you want this application to behave like a really cloud system, we must be able to destroy it, deploy it without losing the system. So we will use, in this case, Docker. This is why we start by a simple one. And Docker is not just a way to run code. It's a way to define what a service is. It's how it starts, what it needs, what port it exposes, and what it depends on. So here we have the repository from GitHub. You can find the example on my personal GitHub here, and you can follow the different steps to run this application in the description. And this application answers one very simple question: what is the current state of the system? In our case, it's traffic light, green, yellow, red. If we think about that as a business application, it can be approved, pending, blocked, as you can see here. And in the real life, that state could be a feature flag, a system health indicator, deployment status, business decision, or even an AI model decision. I made this app very simple on purpose because complexity hides sometimes architecture problems. When you strip everything down, every system is just two things: something that decides and something that remembers. So this web application is like our brain, and the state will be the memory. So instead of manual wiring infrastructure, we are going to let the platform do the work. So here we have an application, our application that already cloned from my GitHub repository, and we will try to generate Docker file. We don't need to write our Docker file. So this session is about the Docker ecosystem. I have other articles that you can see in my Medium blog, my personal blog, that allows you to see how you can write Docker file from the beginning to optimize it. And here we will generate Docker file and compose definition from Visual Studio Code. As you can see here, we use it Docker init. Docker will inspect the project as we have .NET 10 application and generate everything needed to containerize it. It will generate for us Docker file, Docker compose file, and we can see here it requests about the port that we need, and we have the compose file. It's a YAML file generated by default. We use it for one or more than Docker file, and we have the Docker file already here. What just happened is important because Docker, they didn't guess. It's just analyze your project and try and find the runtime. It asks you about the ports. It gives you the port by default, the entry point, and how the service should be started. This is exactly what platform engineering looks like. The platform understands the workload and generates in infrastructure. And we didn't try this YAML file or any Docker files from scratch. We just described our application. We started from a basic application, .NET 10 application, and the platform produced a service definition. Now, we already created our Docker file, and Docker understand our application. Let's discover now. So we use Docker Compose app to build the API image. We have Redis. We will start it also. We connect them and expose the application. That's no longer just running code. That's bootstrapping a system. So with just one command line, we use a Docker Compose app. And if we go to check that in Docker Desktop that already installed in my machine, we will see the different images, containers that already generated from my application. Here I have the image that already created, and from this image we have the container. So this is the default name given by the Visual Studio, and we have the link of application. So we use a default port, so it's localhost 8080. So what matters here is not the UI, our user interface. What matters is that our application now presenting as an image, we have running container, and we have service in system. And in Visual Studio, we are able also with the Docker extension to see our image, and even also we have also the container. Our container will be displayed also. And the image we have latest is the tag that we already used it here. And as you can see here, we have the tag, the ID of the image. Now let's check now application running as a container. We will use this link to see how it works. So now we have this application, but it's inside our container. We can see here, so we change the status. We have the green, the yellow, the red. So it's the same thing as it's the same thing. If we are on localhost without containers, this is our application. Now we launch this application from the container. So one of the most frustrating things in containerized development, specifically for developer, is debugging Docker builds, specifically debugging your Docker files. If sometimes we have a problem, we are not able to build your image because I have a problem in the Docker file and the message doesn't represent anything significantly. So the developer is sometimes try to get pass a lot of time to debug or to understand the error. So traditionally, when you build files, you edit the Docker file, you need to rebuild, to wait and repeat, so it takes time. But this extension will help you really to debug line by line. It's new experience from Docker that help developers to check where the problem is and to understand why the image or the build fails, for example, in this case. Now that we have debugged and validated our container image locally, the next step in any real production workflow is very simple. Ship it to the cloud. I will show you how to extract image. We just debug it in is push it to Docker Hub. So we debug our application. We start with Docker Hub. So no rebuild, no reconfigurations. We will see that. Let's open the container here, extension, and latest is our tag, similar like version, similar to version here. And we are able to create more tags, which means more images, but different tags. Here, for example, I created another image. It's like a copy from the latest image, but with another tag. Now, if you'd like to push up this image to a registry, we start with Docker Hub. It's a public registry. It allows you to share your images, and you need to have an account, as I said before, so to be able to share this image publicly. And you are able to create only one private registry in Docker Hub if you are using a free account. Now, right click, we choose the push. Next, you select your account and you are able to update also the tag. For example, it's for development, for production. So you give a name for your tag, and this and your image will be pushed, let's say deploy it in the cloud on Docker Hub. It will be public one, and here in my account here, I have already an account on Docker Hub, and we can see here that it's a public and this is my image, and explain how you can push this image. Anyone can use this image. For example, we need to add a description, so to explain more about your image that can be used by others. On your Docker desktop, you are able to see on your image in my up in here, and you can find a lot of images already deployed. As you can see, also it detected the vulnerability. You are able to use Docker Scout to check if your image is secure or not. So, and you are able to view it on Docker Up. Now, in this demo, we will show how with Visual Studio become our full container control center. So we are able to build, to store, deploy, all in the same place. And now we'll deploy our image on Azure App Service, but we need to push our image in Azure registry, Azure Container Registry. We'll see that it's a private registry in Azure. And next we will use this registry in web application, that's Azure App Service. So I already created a container registry, Azure Container Registry. It's a really simple click. So we give a name to a registry, and here in settings, to be able to access to our registry from another service in Azure, I just activate the admin user, else your image can't be used by any other Azure service. Now let's go back to our Visual Studio Code. We have already installed Azure extension. We need to define to connect to our account. Let's say our Azure account. You can have one and more accounts. And now I will connect to Azure registry. We disconnect to be able to reconnect again, as you can see here. And now we will push this image on Azure Container Registry. It's the same thing as we did as for Docker Hub. The difference is that we are going to Azure. You can have the same thing for any other cloud providers. So we use that. We need to connect to the registry. If you have internal registry already configured, you can also configure it here. You add just the registry and you push it. As you can see here, we are pushing our image in on Azure Container Registry. Next, we will check here our image, if it's already here or not. We go to repository here, services, and repositories, and our image already here. We can see the name, the tag, the date, everything here. So you can have more than tags here, more than image, and you are able to select what you need as an image. Now we will create just Azure Web App, it's Azure App Service, to be able to see the container here. So this is the traffic resource. So I get the same resource group, we give a name, and we select, in this case, container. It's one container. We are able only to deploy only one container. So else, if you need to have more than container, you need to use Azure Container Apps or Azure Kubernetes Service in this case. So I need to define the image, as you can see here. So I try to access to Azure Container to find my image with a tag. I can have multiple images, but every image is related to that specific tag. And I deploy my image in this case. So I don't know if you have any questions here. So this is I complete my time, I guess. I don't know if you have any question about the session.
Any questions, anybody?
Great job.
Thank you.
Yeah, I made a great job, and the demo worked out perfect.
Are you using Visual Studio Code in the browser or the Visual Studio Code app?
App.
Okay.
But you can do the same with Visual Studio or using the browser or GitHub. So you can have the same thing. The same extension exists.
Cool.
Cool, yeah. I'm not too sure if Harry can hear me there. Harry, are you on there?
If I can get extra time, can I ping my virtual machine right now? I think I'm able to get it up right now.
Sure, do, yeah, yeah. I have your
Okay,
screen
thank
here
you.
as well. I'll just put it up now.
Go for it.
Okay,
And Amina. Okay, Precious, your screen is up.
all right, thank you. So this is my VM1, which is in East US. And this is my VM2, which is in West US. So I'm going to confirm the IP address of this to be sure we are pinging to the right VNet. Then as well confirm our connectivity if these two resources in Azure are actually communicating. So this is our IP address here on this VM, and this is so now I'm going to ping this, but before I go ahead with to ping the this other VM in East US, I'm going to try and enable the firewall, the private firewall, not all, just the private firewall, because by default the VM's private firewall is going to block the connectivity. That is one of the constraints around the pinging of VM through when you do the configuration. So I'm going to first of all disable the firewall first. I'm doing this on PowerShell in case I missed saying that earlier because I borrowed the time I'm using to do this right now. Okay, okay, profile. No. Yes, I can do it. Thank you. Right, profile. Trying to run this command to be very sure of what I did. Private. Language. Okay. I just disabled the firewall here. I'm going to go over to this VM as well and disable the firewall, the private firewall there as well. Firewall. Okay, I'll go ahead and ping the VM. This is this. Okay. I'm trying to ping the IP address of this of the VM in this VM in West US. This is the IP address. Trying to ping it properly. Let's see if we are going to have a proper connectivity timeout. I hope nothing's blocking it. It's lost. Maybe I can do it here to confirm it. Confirm if the VM is turned on. That's what kind of. The VM, the VM is not communicating yet, and I believe there must be something stopping it from communicating, which I'm going to figure out right now. Let me be sure. I disabled the firewall. Enable. This firewall. I'm sharing. Echo. I don't think I'm going to continue doing this right now. Maybe
Okay.
on my own, I'll try and figure out what it is that is stopping me doing this.
No problem, Precious.
Yes.
So, Harry, can you hear us there? Harry, I can't hear you.
Frank, can you hear me?
Yeah, I can hear you now. Yeah, yeah.
Awesome, thank you.
Do you want to share your screen there with us?
Oh, sure. Yep.
Sorry for the delay.
Sorry about that. Even I had, connectivity issues on my office laptop, so I had to switch it to my personal laptop.
Okay.
Can you please confirm if you can see my screen, Frank?
Yeah, there you go.
Excellent. Okay. Thanks, everyone. Good afternoon, good evening. So in today's presentation, we'll briefly talk about the challenges faced by the capital-intensive industries like ours, where equipment reliability directly impacts safety, production, and profitability, right? So we'll also briefly talk about how traditional maintenance approaches are no longer, the right way to do that, and also, you know, competitive data-driven environment in this world, how AI and cloud automation would be transformational enabler that would shift reliability from a rather cost center. Always, this used to be treated as a reliability used to be treated as a cost center. Rather than that, it is going to be a strategic advantage. So today's journey, we'll go through the limitations of traditional maintenance, then move through a vision enabled by AI and cloud technologies, and also the transformation and the results, the cultural changes as well. So our company has transformation in capital asset management strategy was very crucial because we have around $8 billion in plant machinery and equipment, and it is the significant portion of the company assets, and it demands unprecedented technological innovation to make sure we are up to date with the maintenance strategies. But this is a little more theoretical because we will be talking through the real world transformation, our story, and it's not just a conceptual framework.
I think I already provided those documents on my slide. So the best practice we just made up one data center.
I hear some background noise. Maybe it's just me or everyone. But talking about the evolution of maintenance paradigms, so we all might have seen at some point in our lives that this transformation happening in the last decade or two. Historically, we have always been used to that reactive maintenance where the equipment failure happens. There won't be any advanced planning, and we try to react and fix that issue. But then with the advent of preventive maintenance, so there we have this calendar-based scheduling, fixed time intervals, usage metrics, and all that came into picture, and the maintenance people started planning the maintenance rather than reacting when the issue happens. And the latest trend or the latest strategies are more onto the predictive maintenance, where you have condition-based indicators, you have the sensors, data-driven forecasting, and planning during the optimal windows rather than planning a downtime as such, and latest highly targeted interventions as well. And now the future is all about the autonomous maintenance and AI-detected anomalies with self-corrections, algorithm-based optimized scheduling, and these are all the latest trends, not in use extensively across the world, across the industries, but people are people have started thinking about it. People have started focusing on how to leverage these latest technologies. So some examples what we might have seen. I would rather take a car we have been using in the last 2 decades. So we have initially seen that reactive maintenance, but then preventive maintenance. So when preventive maintenance is happening, we always go by the schedule, like, even now we do for most of the cars. Like, we go by 5,000-mile maintenance schedule as prescribed or as recommended by the equipment manufacturer. Okay, at 5,000 mile, what all needs to be done? At 10,000 mile, what needs to be done? So on, right? And this works fine. But what this also brings is unnecessary parts change. Okay, you take your BMW to, you take your car to a service provider for a oil change. They would come up with a recommendation, or they would say, you need to change the filters, you need to change 100 different things. Whether we don't know whether they are really required or not, because we don't have a visibility of the exact usage, and we go ahead and get those changed. So this is just a car, but in real time, in heavy equipment industries, these cost a lot. These are the significant cost factors in the overall company maintenance strategy. So as we move towards predictive maintenance and autonomous maintenance, what's happening these days is, if we have seen the latest electric cars or technology cars. I drive one of the technology cars, so I know a little bit about how AI is being leveraged. For example, it does check the battery modules, it does check the motors, braking systems, and this continuously keeps checking and analyze the real-time telemetry and detect early signs of potential component wear and tear or failure. And sometimes, if it is a software thing, it even push over the air or OTA software bits or updates that could fix and mitigate the issues remotely. So these are the recent happenings in the industry. Like, it can be automotive industry or also mechanical industry. So the traditional maintenance dilemma we always had is fixed time-based routines. These all always work fine. These are industry driven, sometimes regulatory requirements. These have to be done. But what is the the disadvantage, or we say, of this kind of maintenance is, regardless of the actual equipment condition, this leads to unnecessary work on healthy assets. Sometimes, the asset is working fine, but we still bring it down to perform a traditional maintenance, like, based on the meter readings or the hours completed, or as recommended by the original equipment manufacturer. So what does is, like, we are doing unnecessary maintenance when it is not required, and we sometimes overlook the fail, and also it ends up with failing to prevent real failures in this journey. So what does this cost? What it used to cost us in a heavy equipment industry, the cost of preventive maintenance. We always ended up, an analysis clearly shows that, we always ended up spending a lot of money on replacing components prematurely, rather than really analyzing in the real time. And also that led to unexpected failures and operational inefficiencies. Now, with the recent innovations happening across the globe, there's a clear shift from that to a strategic vision, like, how maintenance can be transformed from a compliance function into a strategic reliability driver. And this is where we see the AI, IoT, and analytics as tools that enabled predictive insights. So what is that is helping us in this journey, right? Asset criticality. So how do we plan this shift this transformation from a reliability industry, right? So first, we normally assess our asset base. Like, we do that assessment of our equipment. Like, what is the equipment base we have, and what are those equipment what is the criticality of that equipment for our manufacturing process? And this is where we start our journey with a comprehensive enterprise-wide assessment to identify and prioritize high-impact equipment across multiple facilities and standardize these equipments and categorize them, classify them, and keep updating all those assets in the systems, in the CMMS system or the asset master or equipment master systems. Identify the patterns, identify the criticality, identify what are all the classification codes that could help in risk prioritization, and standardize these across the plant. That is very critical, because when we come up with the risk, maintenance strategies, we can't implement a maintenance strategy to one asset every time. So this needs a standardization across. Like we have maybe 10,000 particular loaders, or Caterpillar loaders, or Elogear, or mobile equipment of hundreds of them, same equipment, or make models. So we want to standardize those so that we can push the maintenance strategies standard across the company, instead of addressing or looking at one particular asset in one of those plants independently. And this Azure powered architecture, how we are getting there, are leveraging the Azure powered architecture and IoT Hub analytics. We'll take a quick peek at this, how our IoT devices in the plant equipment are connected to the IoT hubs, and then the analytics and on the cloud, and then how our AI-assisted tools provide actionable recommendations while updating our ERP and automating the work orders and inventory management solutions here. Here we have actually identified 4 critical layers in the manufacturing. Like, the level 0 or the core is the sensors or actuators, which are directly connected or tied up to, or integrated with the real equipment there. It can be to the mobile equipment, it can be to the fixed equipment in the plants. What they do, sensors and actuators, they do send the temperatures, vibrations, torques, and these kind of analytics. So these are the data crucial to understand how the plant is, how the piece of equipment is actually behaving, or is trying to tell us. Like, it's like a human, like, when you're about to get sick, okay, you do kind of send some signals, like, your temperature or some kind of those kind of attributes, parameters. You send same with the piece of equipment as well. And we have the control devices like the PLCs, CNC controllers, and the robots, right? And then this is where the Azure IoT Edge or the local analytics help in monitoring and supervision. And then the next layer is the IoT Hub, where your analytics come into picture. And when it is talking to our ERP systems, that's where it would recommend, like, what is the action that would be required. And the ERP takes the corrective action in generating the work orders, in generating any CBM alerts and those. Any questions so far? I know it is a little more theory than any other presentations.
No, you're good. There's no questions coming in here on my side.
Okay, thank you. So what does Azure IoT Hub does for us? So Azure IoT Hub is managed a cloud gateway that securely connects equipment like our machines, sensors, PLCs, gateways to Azure. And it's actually built for high volume, because these heavy equipment keep transmitting hundreds and thousands of data elements every minute. So these are actually built for high volume, low latency telemetry ingestion, and typical equipment data. Equipment might send, like, temperature, vibration, pressure, voltage, RPM, and some error codes as well from the OEMs. And how this messages might look like is that this is one of the very simple JSON messages. It might look like what is the date time stamp, and the machine ID, the temperature, what it is at that point, and the vibration and the pressure, let's say. So these are the analytics we keep sending to the hub, and then the models actually keep analyzing these data and then talking to the ERP, and then based on the recommendations, it would be triggering the alerts to generate a condition-based maintenance alert or generate a work order based on the configurations. So this is how our integration works with based on the analytics to our CMMS system, whether it can be an SAP, Oracle, Cloud Fusion, or JD Edwards. Any of these maintenance systems would be actioning based on these predictive alerts in creating the work orders, automatically eliminating manual process, and also it does recommend the spare parts that might require that might go into this piece of equipment at that for completing that work orders. And based on, we are in the POC, it's a very early stage, it's new to the industry, but whatever the lessons we are learning, the path for reliability excellence is assess your readiness. Okay, these current maintenance practices you need to analyze and evaluate. Where are we? Are we ready to identify and transform these opportunities? And it might take an year or 2 years just for that assessment of the readiness before you kind of even get into the architecture more, like where you can leverage Azure AI IoT and analytics and build your reliability platform. So that's your success or anyone's success who wants to get into this journey from reactive to proactive maintenance or reliability centric maintenance transform from is actually very crucial to identify your readiness to this program. And that's all from my end. Any questions, Frank, and any questions from anyone of the team or group here?
I just have one question myself there. When the IoT device is sending messages to the hub, is that where all the costs come in, or how many
Yes.
messages?
Yeah. So Frank, you might know these sensors, IoT, sensors are very expensive. That's where we are talking about identifying the criticality of the assets. You can't put these sensors in all, like we have probably close to 30,000 pieces of equipment, whether it is small, big, and all. So we each and every IoT or sensor, they are super expensive, so we can't put. So that's where you identify which of your critical equipment is, and then start your maintenance strategy from there. Like when a piece of equipment comes down, what is that costing to the organization? That's where the main cost is. And also the of course the IoT related costs. I mean the hub, and these are not, I mean today they are expensive, but over a period of time these are going to come down significantly. But those sensors and IoTs, they are still expensive. We have been seeing over a period of time it is still expensive. Each sensor or each IoT device are still expensive.
Okay.
Great job. I loved the analogies to like electric cars and maintenance. Those were great analogies.
Thank you, Dan. Thank you very much.
Yeah.
Yeah, I don't think, like, we had another speaker, but he hasn't turned up. So I don't know. Amy, have you anything to share with us? Amy Diamond, are you still with us? No, so we're in 35 minutes into the show, so I'm just going to end the live show. Thanks everybody for joining us this week, and we'll be back again next week at the same time. So thank you.
Thank you, everyone.
So